Hello, and welcome to WinHEC. I know that this seems like a very strange transition from how do you get into a small device to how do you do networking at 100 gigabits per second. But that's where we're going next. With the lights, it's a little bit difficult to actually see those of you who are out there, but let me start with a couple of simple questions. How many of you are actively involved in developing drivers today, networking drivers? 1, 2, good. I'm glad there's somebody here who cares about this topic. But we're going to make it so that the rest of you care about it before this time is over. Let's get started. We're going to talk about optimizations and offloads. What's an optimization? Any ideas? Shout it out. I can't see hands. An optimization is when the network operating system, when the Windows operating system does something in software to make things go faster in the networking stack. So what's an offload? An offload is when we ask the hardware, the NIC, the network interface card, to do some processing for the Windows OS. And we're going to look at some examples of how that works. Finally, would you ever use these things together? Sure. Sometimes we do some things in the operating system that take advantage of capabilities that are available in the hardware on the NIC, and they work together to bring better results. So today we're going to talk about what that's all about. At the end of this, you should have some understanding of both how NICs have evolved, what they can do today, and what our vision is of where we're going to be over the next 12 to 18 to 24 months. So, hardware offload capabilities. These are what we refer to as offloads. These are when we ask the NIC to do things like address checksum offload. Most of you, at some point in time, had a class in TCP or IP networking in school, and you might remember that in the packet headers, there's checksums to make sure that the packet is received correctly. It's wonderful that today we can assume that the packet hardware, the NIC interface card, will automatically calculate the checksum on the incoming packets and tell the operating system whether or not the packet was received correctly. Not only that, but on the way out, when we send a packet, we can ask the NIC to automatically calculate and insert into the packet the right checksums for the TCP or UDP and IP headers all the time. This cuts down the amount of work that the operating system has to use, the number of CPU cycles per packet that we have to use in header processing for packets. Interrupt moderation is another interesting technology. These have all been around for quite a while, but perhaps you're not familiar with them. Interrupt moderation comes from back in the days when every time we got a packet, we got an interrupt in the operating system. That cost us a lot of time going in and out of interrupt processing code. Now, however, with the help of your NICs, that buffer can be gathered up on the NIC, multiple packets can be collected, so when we get an interrupt and have to switch context to an interrupt handling routine, we can process all the packets that come in off of the NIC at the same time. It means a lot less context switches and a lot less CPU overhead from the context switches. Jumbo frames. The most expensive thing in the operating system to do is process headers. Then if we can get bigger containers, think of it as shipping on your trucks. If instead of shipping lots of little boxes, each one of which has to be individually handled and delivered, we can take all of those and put them in a great big box and only have to process the delivery once, then we can make things far more efficient. And that's what jumbo frames do for us. At the switches in the network, at the NICs in the end system, and in the operating system processing code, jumbo frames reduce the amount of time we have to spend doing header processing. Large send offload helps us when we send. We can take a very large packet, up to 64,000 bytes long, hand it to the NIC, and let the NIC chop it up into small packets that can go out on the network. Again, the operating system doesn't have to spend its time chopping up the packets, doing lots of headers, calculating all the checksums, doing all the other pieces that have to go into every header. And finally, the other side of being able to process the large sends is being able to do large receives. The packets come in off of the network, but they come in very quickly, and the hardware can look and say, these two packets actually are two sequential packets in the same TCP flow. With RSC, receive side coalescing, we can take those packets inside the NIC, convert them into a single larger packet with only a single header, and it reduces the amount of header processing in the OS. We also have software-controlled features, and we're going to get into many of these a little bit more as we go on, so I'm going to spend a little less time on these. Data center bridging. Data center bridging is a technology that was first invented for fiber channel over Ethernet. Fiber channel needs a technology where it can send packets in a lossless environment. As you may know, Ethernet is not a lossless environment, although these days with fiber and high-speed switches, it's much closer to that. DCB then is used to make it so that we can have some packets going in one lane of a highway where there's no accidents that can occur, and all the other packets can fight for the other lanes of the highway, and if they have an accident, we just resend them. Encapsulated offloads. How many of you are familiar with network virtualization? No, not too many? Network virtualization is when we start allowing each tenant in a hoster to have their own network. It's like VLANs on steroids. We can take and let each tenant network go in its own special virtual network that doesn't require VLANs. It can be switched at a higher level. So with technologies like NVGRE or VXLAN, we can make it so that we can map a customer's transmissions to staying within that customer's private network, even though they share the common hardware infrastructure. IPsec task offloads allow us to have the security associations for an IPsec session put into the NIC. RDMA is something we're going to talk about and demonstrate later on. Remote DMAs allow us to move packets from one host to another without going through the CPU of either one. RSS, SRIOV, both technologies that allow us some accelerated processing, and we're going to get into these more in depth. VLANs, I'm sure you're all familiar with. Again, something we asked the NIC to help us with. VMQ and VMMQ we'll cover in depth later on in this talk, so we'll come back to those later. And finally, things that we do just in software, where we don't use the NIC. We use access control lists. Places where an administrator can say, this VM, for example, can only talk to these addresses. Or it can talk to every address it wants to except for this list. NIC teaming. We have two kinds of NIC teaming we deliver in Windows Server today, LBFO and switch embedded teaming. And we'll talk more later about switch embedded teaming, the new teaming solution we have. VM QoS. SDN QoS, the ability to manage bandwidth on a per VM basis is very important for many customers. And finally, virtual RSS, the ability to have multiple queues or multiple lane highway between the Hyper-V switch and a VM so that we get processor parallelization inside the VM. Again, something we'll talk about more later on. I've been in this industry for a little while. You might not tell it because I'm still looks like I'm 22 years old. But back when I first started writing networking drivers, we did it by getting a UART. Some of you might remember that technology. And we programmed 1 byte to the UART, and then we interrupted the card. And when bytes received, we got a 1 byte register. We got interrupted. We had to unload the register and reset the interrupt so that the NIC could tell us about the next byte that came in. I did this even with ISDN drivers back in the 1980s. Very slow. You couldn't do it with today's speeds. It just wouldn't work. So we've moved a long ways from those first NICs where we unloaded and loaded the NIC with 1 byte at a time to today when we offer these great big packets, great big buffers that we can handle, whole pages of memory we can hand to the NIC and let it process it. The only thing that the NIC did for us in those days was when we signaled that it was the end of the packet, it would generate the cyclical redundancy check, the frame check sequence, and put it onto the end of the packet so that the Ethernet frame existed. But they got a little more sophisticated, and pretty soon we weren't just loading 1 buffer in, 1 byte in, and 1 byte out. We started loading 1 packet in and 1 packet out. But there was still no processing that went on in the NIC. Everything had to be done in software, and you handed it the buffer, and it sent it with the FCS check, and that was all that happened. Some of them at that point began to say, oh, I can do the header checksum, and we started taking advantage of that. By the time Server 2008 R2 came along, we had a few more technologies. We could do RSS, receive side scaling, which allows us, as we'll see in a moment, to spread the processing across multiple CPUs. Up until this time, we didn't need technologies like that because computers didn't have but 1 CPU. And as we started to get into multi-core machines, we said we need to take advantage of that. So that's what we did. And then when we got to 2008 R2, we said, and we can do that same kind of thing for VMs in Hyper-V. So let's talk about what RSS does. In the early NICs, everything that came into the NIC came up through 1 pipe into the OS. TCP swallowed from 1 pipe. It worked well enough. 1 core could keep up with 100 megabits per second. Everything was pretty good. But then as speed started getting faster, we just said, this isn't good enough. We need to be able to take advantage of our multiple cores in the OS. And so what we did was we said, with receive side scaling, we will hand you, NIC, a set of interrupt vectors. And we want you to use multiple queues. Whenever a packet comes in, calculate from the packet header which queue it belongs in and stick it in that queue. And all of the packets associated with a particular connection will always end up in the same queue because that's how the calculation works. Because it's all going in 1 queue, I know that I don't have problems with out-of-sequence packets, which would kill our performance. Instead, we can deliver those packets from different flows into different CPUs, different cores, process them in parallel, and today we see this operating into the tens of gigabits per second without any problem, which is good because today we need to be able to process those speeds. So we finally get to Server 2012 R2, and we discovered that some of the NICs now have switches on board. I should note that the technology that you see back here is pretty much the current state of the art of many of the 1 gigabit per second and slower NICs that are in the market for client machines. They're essentially just delivering packets up in 1 path. As we move to mobile broadband 5G, as we move to the latest Wi-Fi speeds, as we move into 10, 25, 40, 50, 100 gigabit per second Ethernet, this won't cut it. So for even a 10 gig Ethernet NIC, we have to get to where we are here. We need that switch. We need the ability to begin to really spread traffic within the switch and filter it there. What this allows us to do then is as packets come in, now that we run more and more in the Hyper-V environment, as the packets come in, we can say all the packets for that VM stick in 1 queue. And the packets for the next VM stick in the next queue. And then when we get an interrupt for a queue in the OS, we know that every packet we get is going to the same place. And we can take all of those packets at once and route them to that VM. It's much more efficient. And because every different queue is being interrupted on a different core, we spread the load across all the cores within the OS. It makes it much more efficient. With the switches, now we can begin to program them, and we can guide where those packets are going. With this same switch capability came along another technology that we referenced earlier, data center bridging. Data center bridging takes that bigger bandwidth that we've got now, say 10 gigabit per second bandwidth, and says, I want to make it into a multi-lane highway. I want one lane for trucks, one lane for buses, one lane for taxi cabs, and one lane for everybody else. Maybe I'll make it a big lane for the rest of the people. But I can do that with data center bridging. I can also set rules with data center bridging that say, in this lane, whenever you see that the stoplight ahead is red, I want you to turn the lights back down the freeway yellow to tell everybody to slow down, so that we don't have everybody running up to the stoplight and stopping really fast. Let's slow down and back off. So, VMQ, virtual machine queues, came along with this spreading technology that RSS brought us. And in the first days, we did everything, as you can see up here, everything by matching filters and putting them in queues. Except for one problem. Many of those early NICs only had 8 or 16 queues. If I have 20 VMs, I could only give 7 or 15 of them their own queue. Everybody else ended up lumped together in the default queue. The problem there was that everybody who shared the default queue had everything intermixed in a jumble in that queue that had to be unpacked in the OS and redistributed, and the performance for those VMs wasn't very good. And even today, we face this problem, and we'll see this as we go along, and how we try to solve it. Once we started getting a switch in the middle, we could go and say, oh, we can use switch technology and assign the ports of the switch to different VMs, but we still have the problem that if we have more VMs than ports, we still have everybody end up in the default queue, which is a single queue, and all of those share it. This really came to a head for me when I was debugging a problem with a customer in Europe who was running on a host that had a NIC with 32 queues, and they had 200 VMs. Well, the first 31 VMs each got their own queue. But VM number 32 through 200, almost 170 VMs were sharing one queue. One queue, one processor at that time, could handle about 3 gigabits per second. If you have 170 VMs sharing about 3 gigabits per second, none of them are getting very much bandwidth, are they? So that's a problem. Okay, so we started saying, how else can we accelerate things? 3 gigabits per second for a queue isn't very much. Even if I have enough queues for all of the different technologies, I don't have what I need to handle a VM that wants 10, 15, 20 gigabits per second, because one queue can't do that if I brought that software queue all the way through with one queue. So we looked in the OS and we said, oh, I can make a multi-lane highway between the Hyper-V switch, where I'm unloading the queue, and the VM. And if the VM has multiple logical processors, I can now do parallel processing in the VM, and I can move the bandwidth up. If I ran the demo that I used to run on this, you would see that with VMQ, I can get around 8 gigabits per second per VM with current processor technology. Not the most advanced, but say standard, what you would buy today on the streets here in Taipei. With VRSS, I quickly jump up over 20 gigabits per second into the VM. The software arrives at the Hyper-V switch. The Hyper-V switch calculates the Toeplitz hash, or we get it from the NIC, and we divide the traffic out into different channels of the VM bus so that it arrives to the NIC as a multi-lane highway. This all gets done like this. So if the packet, in this case, let's say it's VMF, it comes in, it matches the filter, goes to F, but as soon as it hits the Hyper-V switch, it gets put into a multi-lane highway to connect to all the different virtual CPUs in the VM. Because there's very little header processing going on in the Hyper-V switch, because remember, the NIC has already said all the packets in this queue are going the same place, all the switch has to do is just divide out the traffic and ship it to the VM. So very little processing in the switch and parallel processing of the TCP stack in the VM, and we quickly see speeds up over 20 gigabits per second. Server 2016 brought us some more technologies. Converged NIC. How many of you are familiar with RDMA? Anybody ever used it? I don't see any hands. Okay, that's all right. We have the switch extension. Hyper-V switch, as you may be aware, actually has a reprogrammable engine so that you can plug in different engines, whether that's Cisco's NFV1000 or whether it is our own Azure Stack extension, or whether you use the native extension, native routing extension that's in the Hyper-V switch. All of those can work fine. SDNV2, software-defined networking, a very important technology for hosters, is something that we improved in 2016. Along with that came SDN quality of service. And SDN quality of service is an enhancement and improvement on the existing VM quality of service that we ship in Windows since Server 2012. VMMQ, as we'll see, is VRSS on steroids. Is in the hardware now instead of in the software. It's even better. And finally, switch embedded teaming. Back in Server 2012, we allowed that you could do RDMA on NICs that were connected directly to the host OS, but Hyper-V switch had to have its own set of NICs. And you couldn't do RDMA on the same NICs as the Hyper-V switch was using. This meant that customers who wanted to take advantage of the speeds and efficiencies of RDMA had to put in multiple NICs to be able to do this. This was expensive. Back in Server 2012 days, as you can imagine, having 4 10-gig NIC ports and 4 10-gig switch ports per host was very expensive. Today, it's much more reasonable. But even so, one of the things we set out to do was say, how do we reduce the cost? And what we did was we created a solution that allows the Hyper-V switch to be RDMA aware, and for the virtual ports that go to the host OS to do RDMA directly through the switch. So that today we can take advantage of the RDMA technology that SMB uses, Storage Spaces Direct uses, by going directly from SMB to the NICs with RDMA, and they're the same NICs that are being used by the Hyper-V switch. Now you'll notice in here I've shown DCB on these NICs, data center bridging. That's because if you're using the Rocky technology of RDMA, you must have DCB installed and operational. It's the only way to get the lossless network that Rocky depends on. However, there's another technology that multiple vendors are shipping now called iWarp. iWarp is RDMA over TCP, and RDMA over TCP doesn't need data center bridging. So it's much easier to set up, much easier to operate, and much less likely to have problems that are difficult to diagnose. The SDN switch extension is the Microsoft Azure virtual filtering platform that plugs into the middle of the Hyper-V switch. It's the same filtering platform that runs in Azure today. It has different layers within that switch extension. It has layers that take care of security policy, like access control lists. It has the VNet layer. That's the layer that does the encapsulation and decapsulation of tenant traffic in software-defined networks. It has the software load balancer and the NAT all in there. And it has a layer for SDN QoS. It also has other policies, and all of these policies get programmed by the network controller. So here's how it works. Flow tables. This is software flow tables, and one of the paths that we're on is the path to getting hardware flow tables. So a packet arrives. We have multiple different layers within the VFP, and our first thing happens is we program down some policy. This is our tenant policy coming down. Now we need to have the policies that the tenant itself wants to have. So the first policy is what the hoster said, here's the rules for this tenant. Here's what we're going to do to make it this tenant's network. Now, the tenant says, oh, but I have some specific things I need to do for my workloads. I need to have virtual interface points that need to be converted to real interface points. I need to be able to set different ACLs in place, different rules for who can talk to whom. And so I program that all in. Now I've got the rules programmed in the VFP, and a packet's going to arrive. So the first packet comes in, it hits the first layer. The first layer says, oh, here's the rules that apply to this packet. It goes to the next layer. Here's the rules that apply to that packet. It goes to the next layer and gets some more rules applied. And in the end, it finally gets where it's going. But meanwhile, the VFP took a look at that first packet, took a look at all the actions that went on with that first packet, put them together into a blob, and said, this is the total transformation of this packet for this flow. And now we will recognize every packet that fits this flow, and we will only do one quick transformation, and then we're out. We don't have to go through all the layers every time after that first packet. So when the next packet comes, it doesn't go through all those. It goes directly to the blob, gets the transformation done, and goes out. Very efficient. When we first started shipping SDN, software-defined networking, we only used the NVGRE encapsulation method. Customers told us that they really wanted VXLAN. We try to listen to customers, and so the very next release, we shipped VXLAN. And today, that's our default encapsulation scheme. We still support NVGRE if you want it, but we now default to what customers told us they wanted most, which was VXLAN. And again, just as with everything else in the VFP, all the policies for this get programmed down by the network controller. One of the layers in VFP is SDN QoS. If you've used Hyper-V, you may be familiar with VM QoS, the policy engine that allowed you to set bandwidth limits and bandwidth reservations for different VMs. It works. It's not too bad. But it has some problems when the amount of bandwidth that different things get is widely different. For example, if you said, for this flow, I only need it to have 1 megabit per second. But for this flow, I wanted to have 1 gigabit per second. VM QoS starts to have some problems. So we came up with a new algorithm working with Microsoft Research that doesn't have these problems. And that's what's been implemented in SDN QoS. We can set the policies for whatever different bandwidth you want for reservations or for caps, and we can balance the reservations by weight or by absolute numbers. VMMQ. So if we start with VMQ, remember getting the packets in and filtering them and saying each VM gets its own queue. And we looked at what VRSS did, where we took that queue and put it into the multi-highway traffic instead of a single lane highway to get to the VM. We said, let's do that now in hardware with our hardware partners. So we have a vPort that we associate with each of the VMs, just as we did with VMQ. We put multiple queues on that, and we use the RSS spreading technology to spread the traffic for that VM between the different queues. So now as I get interrupted for a queue off of the hardware, I know it's actually one set of flows for one VM. And I can actually do parallel processing there. We did a demo back at a conference about a year and a half ago where we demonstrated with one of our partners that their standard NIC with VMMQ could deliver 50 gigabits per second into the VM, and it was only using less than 50% of the host's CPU power. Think about that for a minute. A VM that can receive 50 gigabits per second of TCP traffic, and you're only using half of the cores that were on that host. How does it work? Again, just like with VMQ, packets arrive, we go through the match in the switch, and they decide where they're going. And you'll notice that each of these ports now has different number of lines. Because you see, maybe VM A doesn't need very much traffic. 1, 2 gigabits per second, one queue is enough. But B is the same. C, however, is a 10 or 15 gigabit per second VM. So I need multiple queues. One queue is good for between 5 and 6 gigabits per second, typically. F, it just needs 2, so maybe it's a 10 gigabit per second VM. But I can give a different number of queues to each different VM based on the workload that that VM needs. And when they hit the Hyper-V switch, each one comes in independently, hits the VM bus, the multi-lane highway, and uses the parallel processing of the VM. Again, the demo showed clearly 50 gigabits per second on a 50 gig NIC. So we were line rate on a 50 gig NIC directly into the VM. I think I need that on my next mobile phone. Okay, we still have a problem though, because we're still limited by the number of cores we have. We're limited by the number of queues that the NIC has on it, because NICs only have a finite number of queues. And we don't see a lot of benefit for VMMQ below 25 gigabits per second. Because again, VMQ can get me up to about 10. So VMQ plus VRSS will get me over 20. So VMMQ becomes useful when I get past that. On the other hand, VMMQ can reduce my CPU power that I need even at 10 gigabits per second. It's just not as big a step. The biggest place this becomes useful is when the number of VMs is more than the number of ports. I mentioned earlier, if I've got, say, 100 VMs, but I've only got 64 queues. With VMQ, the first 63 VMs get their own queue, but the last 33 VMs share that queue. That's a problem, because those 33 VMs sharing the queue are not going to get good performance. With VMMQ, I could say, okay, the first 60 each get their own, and the rest of them share 4 queues. Well, now I have a better number of VMs to queue ratio than before. I could even take it down further. I could go all the way down and say only the first 50 get their own queue, and the next 50 share 14 queues. That way, I could really get some parallel processing going on. Back in Server 2012, we shipped our NIC teaming solution in Windows. It was very well received, is very widely used today. But as we began to look at more and more stateful offloads for VMs and more cases where networking really needed to be integrated with a Hyper-V switch, we realized we needed a new teaming technology that was fully integrated into the Hyper-V switch. And that's when we released in Server 2016 switch embedded teaming. Switch embedded teaming is designed for those times when you're doing something that requires stateful offloads, or you're doing something with the VM switch specifically. Now, the Server 2012 NIC teaming solution, LBFO, isn't going away. Not anytime soon. It's still there. And it does some things that switch embedded teaming doesn't do yet. And so you still need them. For example, if you have switch embedded teaming, that only works if you've got a switch. If you're in a native host, you don't have a switch. You need to have LBFO available to do your NIC teaming. But if you're in a Hyper-V environment, and especially if you're using a stateful offload like RDMA or SRIOV, you need to have something that's fully integrated and aware of the things going on in the switch. And that's where switch embedded teaming comes into play. Server 2016 was a V1 of switch embedded teaming. As we progress, you may see more and more capabilities being shipped there. But today, it doesn't have everything that LBFO has. For example, it doesn't have LACP, which is something a lot of people like to use. But LACP is technically incompatible with stateful offloads. So we chose not to focus on that with switch embedded teaming. LBFO still provides that, and so we have a solution if you want to run with LACP. So what it does switch independent teaming. That means that the switches involved don't have to know that you have a team on the host. It does dynamic and Hyper-V port modes. We recommend Hyper-V port modes now because as we move to faster and faster ports, if I'm teaming a couple of 25 gig NICs, NIC ports, then I don't need the same services that I did when I had a bunch of 1 gigabit per second NICs. It's RDMA and DCB aware. It knows what traffic channels are, and it knows how much bandwidth the Hyper-V switch can use and how much is reserved for other purposes. It does teaming in the face of SRIOV, and even does failover with SRIOV, where it will reinstantiate a new VF in the VM, a new virtual function, if the virtual function on a NIC that went down was there to start with. And it will team up to 8 ports, although what we see as we move to these higher speed NICs, most people only want 2. A couple of simplifying assumptions were made for our V1 solution. The first one is all of the NICs that are in the team have to be the same make and model. And that way we don't have to worry about trying to match capabilities between them. We don't have LACP because, again, LACP isn't compatible with SRIOV or RDMA. And it doesn't have active-passive teaming like LBFO does. Because while active-passive teaming made sense if I was teaming 100 megabit per second or 1 gigabit per second NICs, it doesn't make much sense at 10 gigabits per second or 25 or 40 or 50 gigabits per second. We released, a little earlier this year, a couple months ago, Windows Server version 1709. It's in our semi-annual channel. It's available for download, and you can play with it. It's got a couple of new features in it that will be there as well when we get to our next long-term servicing channel. The first one is dynamic VMQ and VMMQ. This is also known as RSS v2, RSS version 2. What is it that dynamic VMQ and VMMQ do for us? We're going to talk about that in a second. The other one we do is guest RDMA. We do RDMA now into the VM directly, so the VM can take advantage of that RDMA. So dynamic VMQ and VMMQ came along to solve a problem. Workloads are not static. You want to keep your networking workloads aggregated onto the fewest number of cores you can. So where VMQ and VMMQ statically assign mappings between ports on the NIC and queues in the OS and CPU cores in the OS, we said, well, when there's not a lot of traffic going on, why don't we consolidate everything down to 1 or 2 cores? And then when the network traffic picks up, we can spread them back out and use more cores for networking traffic. This way we have less issues of inter-processor communication, everything goes on more efficiently, and we can get things done. The problem was that when we tried this the first time in Server 2012 R2, we got the algorithm, let's just say, suboptimal. It didn't work as well as we wanted it to. It coalesced down very well, very quickly. When traffic died down on the interface, we reassigned core allocations and we brought it down. But we came down too quickly because a lot of times traffic started fluctuating very much. You have a big burst, and then we have a little bit, and then we have a big burst. And by coalescing quickly and not being quick enough to re-spread the traffic, we discovered that when the traffic picked up again very quickly, we didn't have any CPU power available to calculate and re-spread the traffic. So with RSSv2, we're now very quick to spread and much slower to coalesce. We spread when we still have CPU power left, when we can still calculate how to re-spread the traffic. Both VMQ and VMMQ today in Windows Server version 1709 have the ability to use the dynamic spreading. The other one we have is guest RDMA. Now, back about 3 years ago, in the Server 2016, actually in the Server 2012 R2 timeframe, we had our first demonstration of 100 gigabit per second RDMA. 100 gigabit per second file transfers that were using about 10% of the host OS CPU power. Now, most of you who are thinking about networking and you're thinking about what it takes today to do 10 gigabits per second and what the impact is on the host CPU are going, oh, that would burn, 10 gigabits per second burns up a lot of CPU power. But we demonstrated with RDMA that you could do 100 gigabits per second and only tax the CPU a small amount. We then took that and, as we talked about earlier, made it available to the host OS to share the NICs with Hyper-V in Server 2016. And now with Windows Server version 1709, even the guest can get RDMA capabilities with the same latency and the same throughput that the host can. We're going to talk about we're going to show a demo here in a moment, and because I wasn't quite sure I could trust my connections back to Redmond to work reliably from here, and as we go on next week into another site and do this again, it was just best to have it videotaped for you. It's very easy for you to set this up and do it yourself. If you want to know how, let me know, and I can walk you through the very easy steps of setting up this demo. What we have is 2 hosts. Host A, which has a Hyper-V switch. It has a couple of host VNICs. These are the virtual NICs on the switch that go into the host OS. One for management, one for SMB traffic. That one's RDMA capable. We have a VM with SRIOV providing a path to the VF. And of course, always there's a software path to every VM in Hyper-V. And host B is just a plain vanilla native host with an RDMA capable NIC in it. When we go in here, the first thing we're going to demonstrate is traffic flowing from SMB over there into host B. Then we're going to demonstrate traffic flowing from the VM into host B. And finally, we're going to end up showing you that we can do both of those at the same time. Now, when we get to the video here in a moment, here's what I want you to watch for. This is host B section down here. Host B will be having its RDMA counters up. Watch them. You'll see the traffic, and you'll see it arriving at host B. host A's direct host, the host partition will be in the window there, and the VM1 is over here in this window. And so we'll start through and we'll talk through it as we go. So the first thing we do is we start in host A, we start our tool to generate RDMA traffic. You'll see 0 counters on host B for right now. It's getting ready and setting up the job, and there it goes. And it's transmitting at very high speeds RDMA traffic from the host through the Hyper-V switch, through the NIC, and over to host B. And you can see host B receiving them. When we get done, which will take a moment here, it runs traffic for a moment. It just keeps sending, and it's about to finish here. And we were successful. So now let's kick it off over here in the VM. And you'll see that the VM can send, and as you're comparing numbers, the VM will see the same data rates as the host did. Now the VM is getting ready to send. And here it goes. And it's sending. And you can see that, again, host B is receiving the traffic. The same data rates, the same low latency, the same lack of CPU. The processor time on the VM is at 40%. And that's not a big VM. And the processor time in the host, you can see, is actually running at about 0.2%, even though the VM is sending all that data. So now we're going to do both of them at the same time. And here we're actually bound by the fact that it's going to spinning media on host B. And because we're interleaving 2 different writes to 2 different sections of host B's disk, if you were looking closely at the numbers, you'll see that we actually get a little bit lower throughput when we're doing both at the same time. If we were writing into a different storage fabric than a spinning media, we could make this go a lot faster. But as is often the case in networking, we get held up by the storage, because the storage is not quite as fast yet as the networking. But stand by, storage is getting there very quickly. And you can see both of them are sending. And there we are. So, RDMA. I realize that most of you aren't familiar with RDMA, but if you are working for a NIC vendor, or if you're working on NICs for servers especially, although clients can also do RDMA, and 40 gig workstations are out there today to do movie processing, CAD/CAM operations, scientific exploration for oil and things like that, where they need lots of bandwidth and big data sets. RDMA is the perfect solution for those. But it's hard. Because DCB, that technology I talked about earlier, that multi-lane highway, it's very hard to get it set up correctly. So customers have problems. Fortunately, iWarp just works. So right now we kind of like iWarp because it has a lot less customer issues than Rocky does. So if you're thinking about what direction to go in, talk to us. There is a new RDMA deployment guide available at the link here on the screen. I know you get a copy of the slides later and you can go and look at it and try it out. So what have we done and where are we going? Well, we shipped Server 2012 and Server 2012 R2, and there we were focused on optimizing traffic in and out of the host. With Server 2016, we began to look at how do we do SDN better, and then we said, now let's start working on accelerating the guest. Let's make those guests go as faster than the hosts. And so we've shipped guest RDMA, dynamic VMQ, and dynamic VMMQ, and we're coming out with better management tools for that guest traffic. We really are focused on accelerating how the guest gets networking done. So, what's our vision? We believe SRIOV is going to be a key component of technologies going forward. Being able to bypass the host and go directly to the VM will be key to getting faster bandwidth in and out of the guests. So we think RDMA everywhere, for SMB, for persistent memory, for NVMe, NVMe-OF. These are all RDMA-based technologies. So we really believe that RDMA will be crucial to the future. And finally, we need your help. We need you to help us build the high-speed NICs that customers want. Today, there are a few vendors already shipping 100 gigabit per second NICs. 200 gigabit per second NICs are right behind the curtain, and faster NICs are being discussed. Join that train. Customers are moving past 10 gig to 25 gig. Let's keep going. If you do Rocky, help us build good diagnostic tools for it. And finally, start thinking about security offloads. If you go back to our vision slide, one of the things you might have seen on there was quick offloads. How many of you are familiar with QUIC, the TCP/IP technology that does secure web communications? You should start looking at it. We need quick support in NICs. We need other security offloads in NICs. So that's what we want you to do. And finally, I want to thank those of you who make NICs for being our partner, for doing the work that we need to do to help us to offload that processing into the NIC so that we can do more things in the host to make the customer experience a better job. Any questions? If not, I'll be at the Ask the Expert session later on, and you're welcome to come and talk to me there. Please complete the evaluation, and thank you for your time today.